Okay, everybody, we're going to do a quick crash course on Redox. Pharrell is here, as you can tell. I'm going to do my best to go through the notes quickly, do a couple of practice problems from the problem set. You can see I got my laptop here, and we're going to stop today at half reactions, and that should give you guys enough to work on for a time. Okay, slide I'm on. Oxidation numbers of elements in a bond add up to 0. Taking the example of calcium chloride, CaCl2. Remember, we pull our oxidation numbers off the reference table. I got mine up here. They are in the upper right-hand corner of each square. Calcium only has one choice. It's +2. Chlorine has many choices. We're going to go with the -1 because, as you know, they have to add up to 0. Now, so these are at the top. Individual elements. And it's not that these have to add up to 0, it's that the totals must add up to 0. And the totals are oxy-state multiplied by quantity, which of course are the subscripts down here. Calcium, there's one of them, +2. Chlorine, there's two of them, -2 because it's 2 times -1. Add these up and you get 0. This was on your midterm, should be review. Let's give another example. No chalk, I'm devastated. So is Pharrell. So let's do, I'm going to start pulling some off the problems. Actually, no, we'll go with the examples. No, we're going to do problem set first. So let's take a somewhat simpler one. All these are kind of tricky, so I'm going to make up my own. Let's just take water, H2O, +1 -2. 1 times 2 is +2. 2 times 1 is -2. Add them up, you get 0. Sometimes you got to do a little bit of algebra in order to figure out what these things are, but if you work from the outside in, usually it's a little bit easier, and that's in the case if you have 3 elements. So let's see what we got. K2 Cr2O7, potassium perchlorate probably, maybe, +1, oxygen, -2. So we got 2 times 7 is -14. 2 from, there's 2 potassiums, +1 each, +2. Now we got to do some algebra. We know that the totals here, again, not these, have to add up to 0. So we have, terrible looking too. A number here. So what number, when you put it here, gives you +2 minus 14 equals 0? Well, let's see. +12. So you got +2 plus 12 minus 14 equals 0. That means the total from chromium has to be, or the contribution has to be +12, and there's 2 chromiums, so I do 12 divided by 2 is +6. So then if the question is, what's the oxidation state for each one of these, it would be +1 for potassium, +6 for chromium, -2 for oxygen. There's another example there in the notes, practice problem number 2. Let's do one more. I'll pull 2 from the problem set. We'll do the first 2. And again, good practice here. If any of this is not making sense, pause the video, watch it back again. Email me if you have a question, whatever you need. So KClO4. We got +1 from potassium, -2. I have these like memorized because I've been doing this for a long time. Of course, where we're getting these numbers for them is right up here. I go to potassium, I look in the upper right-hand corner, I see that it's +1. Don't know what chlorine is here because there's a million choices. Oxygen, we're going to go with -2 because it's the only choice there. Now, again, from the reference table in the corner, totals at the bottom. +1, -8, 1 times 1 is 1, 2 times 4 is -8. Sorry, -2 times 4 is -8. These totals have to add to 0. We don't know what chlorine is. What can chlorine be? Well, what number, +1 -8, what number has to be here for the total to be to 0? Obviously, +7. So the answer is +7. I go to the reference table and check, and I see, yep, +7 is a choice. We're good. Now, one thing I want to bring your attention to. You'll notice in the upper right-hand corner of the key, it says carbon -4 +2 +4, and then it has an arrow, and it says selected oxidation states. Now, selected. If you go to a chemical reference book and you look up what are all the possible oxidation states for all these elements are, you're going to see a much bigger list than the ones that are listed on the reference table. Hence the word selected. These are the ones that they chose to write on there because they're the most common ones. Now, there is a contradiction within the reference table. Classic example. Let's see, let's try this one. H2O2. You'll find this stuff in your medicine cabinet very likely. Hydrogen peroxide, difference from water because it's got an extra oxygen on there. It's photosensitive, which is why you see it stored in a light-proof bottle. Now, in this example, hydrogen is +1, total is +2 from hydrogen. What does oxygen have to be in order for it to be equal to 0? Well, it has to be -2 total from oxygen, which is -1 each. Now, if you go to the reference table and you look at oxygen up there, the only choice for oxygen is -2. This is where the phrase selected comes in. Selected. It is possible for oxygen to go to -1, and it does, because if you look at table E, I think, you'll notice that the O2 -2 is the peroxide ion. Again, your table of polyatomic ions, which means oxygen has to go -1. Now, for some of these problems on the problem set, you're going to see a couple of exceptions where we talk about selected oxidation states. You might find one that's a little bit hokey. That's fine. Know that it means selected. On the Regents exam, on my tests, you will not have to find any oxidation states that are different than what are on the reference table itself, so don't worry about it. Just be advised as you work through these. Okay, back to the notes. Redox reactions. As you know, in chemistry, any chemical reaction is the electrons moving around. They're being given from one thing, they're being taken by another. All chemistry, all chemical reactions are electrons moving around. So with that in mind, redox is the study of how these electrons move from one type of element to the next. With that in mind, the oxidation numbers tell you the tendencies that these elements tend to have when they participate in reactions. So for example, group 1 is a very easy example. Lithium, going back to atomic structure from earlier in the year, lithium is 2-1. I'm pulling this from the electron configuration at the bottom of the square. Lithium bonds with, say, chlorine. Chlorine is 2-7. Nope, 287. So when lithium takes its one electron, gives it to the chlorine, makes LiCl, now we have lithium, which is a +1. Chlorine now is a -1. Hence the oxidation numbers of these elements when this happens. So when lithium gives its electron to chlorine, this is a redox reaction. We're going to go into the mechanics of how this works in a little bit. For now, just know this saying. Going to the next slide on the notes, we have redox reactions and Leo-Gur. Now, two things that you must remember. Leo Ger. And I'm not going to write it here. You'll have to take notes from the slide. Lose electrons, oxidation, gain electrons, reduction. Another one you can listen to or remember if you want is oil rig, if you are so inclined. Oxidation is losing, reduction is gaining. Use the one that works best for you. So, when an element is oxidized, it loses an electron, and the oxidation number goes up. Going back to the example of, I'm going to give you another example, table salt. Sodium, 281, yep. Chlorine, 287. One wants to get rid of the electron, so it does. It gives it to the chlorine. Now, looking at this mantra here, and again, I'm going super fast. Pause the video, look at the notes, rewind, use YouTube to your advantage. When metals lose electrons, they are oxidized. Well, when any element loses its electrons, it is oxidized. When any element gains an electron, it's reduced. It just so happens that it's more common for metals to lose electrons because, again, review from earlier in the year, low ionization energy, low electronegativity. It's easier to lose one than it is to gain 7 in order to achieve noble gas configuration. I could go on, but I won't. So chlorine gets the electron, goes to 8. Now we have the sodium, which is 2,8, chlorine, which is 2,8,8. Now, lose electrons, oxidation, gain electrons, reduction. So what happened? Sodium lost an electron. It is oxidized. Chlorine gained an electron. It is reduced. I'm going to put a line here. Okay, so lose electrons, oxidation. Sodium lost the electron. Chlorine gained the electron. The sodium's oxidized, the chlorine's reduced. You don't need to be able to, well, I mean, at the end of the year you will, but for now, for this unit, you don't necessarily need to know these electron configurations, but I'm just writing them up there to give some context. So this is oxidation, this is reduction. Okay, now, when sodium bonds, the oxidation number, I should say, when it forms this thing, NaCl, the oxidation number is now +1 and chlorine is now -1. All right, I'm going to stop and say something I should have said before. If you have an element by itself, the oxidation number is 0. So, example, sodium, metal, alone, it's 0. Noble gas, helium, 0. What about a Hofbrinkel, like, say, fluorine? Even if there's 2 of them, the oxidation number is 0. If it's by itself, it's 0. So if you have a lump of sodium by itself, again, the oxidation number is 0. When it bonds, it goes to +1. Chlorine by itself, oxidation number 0. When it bonds, again, goes to -2. So with that in mind, we can look at the oxidation numbers and in doing so, keep track of what's oxidized and what's reduced. So you can see sodium now, sorry, I'm going to go back to this, NaCl, +1, chlorine now, -1. This has been oxidized, this has been reduced. Quick thing I can tell you that's going to help you remember. So you can write this down. One of these things you should write down over and over to practice. If the oxidation number goes up, it's oxidized. If the oxidation number goes down, it's reduced. Oops. Okay. Moving on in the slides. So let's look at a reaction. Well, let's look at the reaction of these two. We have sodium metal reacts with chlorine gas. They react to form table salt. Should we balance this thing? Sure. Balanced. Okay, now, if it's by itself, what's the oxidation number? That's right, 0. So sodium by itself, 0. Chlorine, is it by itself? Yes, even though it's a Cl2 and it's a Hofbrinkel, oxidation number is still 0. Now, when they bond, again, oxidation number goes up, sodium +1, chlorine, oxidation number goes down. Dang it, there we go, -1. So now we can see which has been oxidized and which has been reduced. Well, the sodium has been oxidized because the oxidation number goes from 0 to +1. Lose electrons, oxidation. We'll talk about that in a second. Chlorine, the oxidation number goes down, so it's reduced. Now, this may seem counterintuitive, but remember, electrons are negatively charged. So if you lose a negative charge, you become positive. Think of a negative person that you may have met before. You surround yourself with all this negativity, you become negative. If you get rid of that negativity, you become positive. So the sodium got rid of some negativity, that is an electron, became positive, oxidation number went up. Chlorine gained some negativity, that is an electron, oxidation number went down. What does that mean for here? Losing electrons, oxidation. Sodium, oxidation number 0, sodium oxidation number 1, must have lost something negative. It was an electron. Oxidation number went up, it's oxidized. Gain electrons, reduction. Chlorine gains a negative, goes to -1, gain electrons, reduction. Same thing here. Oil, oxidation is losing, reduction is gaining. I know I'm going super fast, talking very fast. Hit pause, watch this again, and we'll see what happens. I gotta look at my timer here, sorry. Okay, we're good. Ooh, ISS coming overhead in 5 minutes. You should get out there and watch it. No, it's too late now. Okay. Let's see. Agents. So reducing agents. Themselves are oxidized. And the oxy agents are reduced. So with that in mind, the oxidizing agent here is itself reduced. That is chlorine. Chlorine is reduced. Chlorine has oxidized. Sodium. The reducing agent itself is oxidized. Sodium is oxidized. It's the reducing agent because it did the opposite. Okay. Now, very quickly, we're going to do half reactions. I got 10 minutes. I'm trying to keep these two a half an hour each. Half reactions. Now, a half reaction is going to show only the stuff we care about in a redox reaction. I got some steps that are on the notes, but I'm going to go through them right now. So let's take a look at this reaction. We have hydrogen and fluorine reacting. H2F2 makes 2HF. HF, this stuff's the Grim Reaper. One drop of this stuff on your skin, it can kill you. Okay, so again, assigning oxidation numbers, 0, 0, +1, -1. Okay, now, half reactions show only electron transfer. And they're only going to show the electron transfer for the thing itself that is oxidized and the thing itself that is reduced. If you have a bunch of other things in a reaction that are not oxidized or reduced, and if you take college chem, you'll learn more about those, we leave them out. So for now, in this example, we don't have to worry about those because the only things that are in this reaction are either oxidized or reduced, but let's take a look. Okay, so we got H2 and we're going to write the charge up there, or the oxidation state, which is 0. It's going to react to 2H plus 1. Okay, now why did I write 2H plus 1? If you take a look at this, you can see we have H2, and we need how many on the product side? 2 H's. You can't start with more hydrogens than you end with, so you got to balance it. And I balanced it by using this coefficient right here. So all I've done is I've copied this. Let's see if this red shows up. Looking at my monitor here. Yeah, it looks like you can see it. I'm writing this. Now, the question is, how many electrons does it take? Sorry, just looking at my timer here. How many electrons does it take? Well, let's see. We have an oxidation. Here's how I figure it out. I say oxidation. How many electrons does it take? So it's oxidation number change times quantity of element. Okay, now what's the oxidation number change? You can see that it went from a 0 to a plus 1, so that's a change of 1. And then how many atoms are there? Well, there's 2. You can see there's 2 hydrogens and there's 2 hydrogens. Okay, oxidation number change times quantity. So that's a change of 1 times a quantity of 2, which means 2 electrons. Now, we're going to write them over here, 2 electrons. I'm not going to write all the notes up here because you have them on the website. Now, why do we write for the oxidation reaction? The oxidation half reaction, why do we write the electrons on the product side? The reason is they are being given away. Think of an exothermic reaction. We just did kinetics. When you have an exothermic reaction, heat is being released, heat goes away, these are going away. Oxidation half reactions write they write electrons as a product. Now, let's take fluorine. Fluorine, again, we're just going to write it as it is right here, F2, 0. Now, going back to our mantras again. Gain electrons reduction. So in order for fluorine's oxidation number to be reduced, it has to gain electrons. Well, how many electrons does it have to gain? We already figured this out from above. It has to gain 2. So I'm just going to write those here now that I've figured out how many we need. What does fluorine get reduced to? Again, I take the coefficient from here, the element, and then just write the oxidation number right next to it. 2F minus 1. Now let's see if this makes sense. I have 2 fluorines. Each one has a change of 0 to minus 1. That's a change of 1. There are 2 fluorines there. Therefore, it must take 2 electrons in order to change the oxidation number of 2 fluorines from 0 to minus 1. It makes sense. Of course, this has to do with the law of conservation of charge, because if hydrogen is getting rid of 2 electrons, the fluorine must be gaining 2 electrons. Charge is conserved. Let's look at a couple more examples. I'll do my best to explain these. Yeah, we got time for both. Let's say we got 2 Mg plus O2 reacts to form 2 MgO. Yeah, that's right, because magnesium is plus 2. Okay. Again, by itself, 0. By itself, 0. Plus 2. Minus 2. Okay. Oxidation half reaction. Again, we're only going to write what's happening to the thing that is oxidized. So we got 2 Mg, 2 Mg. Write the charge. All I did was just copy this down. Oxidation half reactions, where do we write the electrons? That's correct, on the product side. So again, write your arrow, 2 Mg plus 2. All I'm doing is just copying this down. How many electrons does it take? Oxidation change times the quantity of the element. Oxidation change is 0 to +2. That's a change of 2. How many magnesiums are there? There's 2. 2 times 2 is 4. It takes 4 electrons. And if magnesium is losing 4 electrons, oxygen must be gaining 4. So again, Leo, lose electrons, oxidation, we write them on the right. So we're just going to copy this again, O2 with a 0. How many electrons is it going to gain? 4. And once you gain 4, let's see, it's 0, 2. So that's a change of, again, I'm just going to write this here, 2, 0 minus 2. That's a change of 2, and there's 2 of them, so it's oxidation change. 2 times quantity. 2 times 2 is 4. Again, 4 electrons. Magnesium is losing 4. Oxygen is gaining 4. Everything works. Let's try a trickier one where we have some other elements in this reaction that are not participating. They are just looking at things casually, not paying attention. Pharrell, we good? I know you guys missed him. I rescued him. All right. So we got 10 HNO3 plus I2 reacts to form 2 HiO3 plus, oh boy, plus, I need my timer. There we go. 10 NO2 and 4H2O. This is a doozy, tougher than you'll see on the Regents exam, but we're going to go for it anyway. Okay, plus 1 minus 2, that's going to be plus 5. This is 0, plus 1, minus 2, minus 6, plus 1, plus 5 again, plus 4, minus 2. If you do enough of these, you'll get good at it so that you can do it like a maniac like I'm doing. Okay. So nitrogen, as you can see, is reduced because it goes from 5 to 4. Hydrogen stays the same. We're going to ignore it. Oxygen stays the same. We're going to ignore it. So all we're going to do is pay attention to the nitrogen, which is reduced, and the iodine, which is oxidized. So we got iodine, I2. It's oxidized, I can see, because the number goes up. It goes from 0 to 5. So we're just going to write iodine plus 5. How many does it change? Oh, we got to have the coefficient from the front. Let's see. It goes from 0 to plus 5, and there's 2 of them, so that's 10 electrons. And again, the nitrogen is reduced. There's 10 of them, 10 nitrogens plus 5 each. And we're going to go to, it's going to gain 10 electrons and go to 10 nitrogen plus 4. We will see you in part 2.